let's investigate the gas laws. Okay, let's look at the periodic table. In the periodic table, we have the atomic number for every element. We have the name, the symbol listed, and then we have the atomic number, which is the number of protons or the number of electrons, the atomic mass. Now remember, the atomic mass is the number of protons plus the number of neutrons. They use the term U to denote an atomic mass unit, and one AMU is 1.66 times 10 to the negative 27 kilograms, or roughly the. Now, let's look at what a mole is. A mole is Latin for the word heap or pile. Basically, it's a chemistry unit, and this is a mole roadmap, which kind of helps you understand what a mole equals. If you have the atomic mass from the periodic table and an Avogadro's number, which is 6.02 times 10 to the 23rd particles, and then you have that 22.4 liters of gas at STP is also 1 mole. So all of these, when I say a mole, are equal. So STP is standard pressure and temperature. Let's look at a problem. I have a flexible container of oxygen that has a volume of 10 meters cubed. Find the number of moles and the molecules that exist in that container. Now I have a 10 meters cubed. This is my volume. So I'm going to convert this. I know that 10 to the negative 3 meters cubed is a liter, and 1 liter is 1 mole. And I know 1 mole of oxygen is 32 grams. How do I know that? Well, O2, there are 2 oxygen molecules. Each oxygen molecule is, we have a mole, 1 mole of oxygen at 16, and we have 2 of those, so that's 32. So I get that if I multiply this out, 10 meters cubed of oxygen is 14,000 moles. Now, to find the number of molecules, I have 14,285.71 moles, and 1 mole is 6.02 times 10 to the 23rd particles. Multiplying straight across, I get that this is 8.51 times 10 to the 29 particles. Now let's look at the factors that affect any gas. Okay, it's the quantity of gas, or N in moles, the temperature in Kelvin. Remember, we always have to convert from Celsius to Kelvin, and Kelvin degrees is C plus 273. The pressure in pascals, and then the volume in cubic meters. There are a number of laws we don't focus on a lot in physics, but there's Boyle's law, which is the pressure of a gas is inversely related to its volume. We get this from the ideal gas law, PV equals nRT. We have the moles and the temperature being constant, and so we know pressure is inversely proportional to volume. If K is our proportionality constant, then we have that PV at any time is equal to K, or P naught V naught is equal to PV. So you'll hear this referred to as Boyle's law. There's also Charles's law. Charles's law says the volume of a gas is directly related to temperature. So volume is proportional to temperature, so V naught is some constant times T naught. So setting that constant equal to V naught divided by T naught, and V over T, and setting the constants equal, we have V naught divided by T naught is equal to V over T. Third is Gay-Lussac's law, which says the pressure of a gas is proportional to its temperature. Using the same logic, we're able to get that P naught divided by T naught is equal to P over T. The fourth law is Avogadro's law, which states that the volume of a gas is directly related to the number of moles in that gas. And in this case, pressure and temperature are kept constant. So V naught is some constant times N naught. By setting these two equal, we have V naught divided by N naught is equal to V over N. Now, when we combine all this, we get basically the ideal gas law. You just put them all together. The number of moles is a constant. So you have P naught, you have PV naught is equal to KT naught. And solving all that for K, I get that this constant is P naught V naught over T naught. So P naught V naught over T naught is equal to PV over T. So you need to know how to use the different laws. If you get confused and you don't remember the names, just take the two sets of equations of the ideal gas law, PV equals nRT, and just put in your constants, and your constants will wind up canceling. Now let's look at an example. Suppose I have pure helium, and it's in a leak-proof cylinder. So this is telling me I'm going to have the same number of moles. The initial position, volume, and pressure is 15 liters, 2 atmospheres, and 300 K. I'm going to change the volume to 12 liters and increase the pressure to 3.5. And I want to find the final temperature of the gas. So P naught V naught divided by T is equal to PV over T. So I solved this for my final temperature. So T naught is 12. P naught is so I wind up with 12 times 3.5 times 300 divided by 15 times 2, or a final temperature of 420 K. The third law, the final law, of course, is the ideal gas law. PV is equal to nRT. R is a universal gas constant of 8.31 joules per mole kilograms. So this is not the case. We don't have the same proportionality constant we've had before. This is a universal gas constant that we have worked through. So the ideal gas law, which you learned in chemistry, is PV is equal to nRT. And we're going to use that in some of our problems. For example, suppose I have a helium balloon. That's a perfect sphere, and it has a radius of 18 centimeters. The first thing I'm going to do is find the volume of that sphere, which is 4/3 pi r cubed. At room temperature, or 20 Celsius, its internal pressure is 1.05 atmospheres. Find the number of moles of helium in the balloon and the mass to inflate it to these values. Well, after I find the volume, I need to find the temperature, so I must convert to kelvins. So 20 plus 273 is 293. Now 1.05 atmospheres is 1.05 times 10 to the 5th pascals. You have to do that conversion. I go to the ideal gas law. PV is equal to nRT. Solve it for N. So N is PV divided by RT. Now I plug in my numbers. Pressure is 1.05 times 10 to the 5th. V is 0.022, 0244. R is 8.31, and T is 293. And I get that it has a 1.052 moles.